Okay, so we're going to go through Newton's 3 laws in basic terms. And then what we'll do is we'll get the official definitions, which is the ones you have to learn. But if we kind of remember it in terms of the way and understanding it, it's much better than just parrot learning definitions. So the first law, I like to think of as, I like to remember it as this first, the one, inertia. And so the first law is that an object at rest will remain at rest unless acted on by a resultant force or by a force. Or it will continue in motion unless it's acted upon. So basically, an object is going to do exactly what it's doing unless something acts against it. Now, this is easier to understand if we think of in space. On the ground, so say on Earth, if you have a ball that's rolling along the ground, it comes to a stop eventually, which doesn't make sense in terms of inertia, because it's saying, well, if it should just carry on. But of course, we know that there is a force that's slowing it down, and that's why it slows down, because friction slows that ball down. So it would have done what it was going to do, what it was doing at that point, but friction acted against it, and that's what stopped it. But in space, things go on because there's no friction in space, right? So if you have a satellite going around the Earth, it just keeps going. Okay, so that's inertia. So inertia, an object will continue at rest or in motion, will continue at rest or in motion unless acted upon by an opposing force. So that's inertia. So objects do as they are doing unless something disrupts it, unless there's a force that stops them from doing what they're already doing. So in other words, if I'm stationary, I stay stationary. If I'm moving, I stay moving. In space, we can easily see that, because if something's flying through space, it just keeps going unless it hits a planet or something. All right, so let's get the actual definition that we have to learn. Can we find it here?
So I found it on page 30.
Okay, great. What does it say?
An object continues in a state of rest or uniform, moving with constant velocity unless it is acted upon by a net or resultant force.
Okay, an object continues at rest. Say that again. An object continues at rest or uniform motion.
Continues in or uniform velocity unless it is acted upon by a net or resultant force.
Okay. So we'll save this as a screenshot. So obviously that's what I said, but we want to be specific with our definitions.
Okay.
Net or resultant force. Resultant force. Okay, so that's inertia. That's the first law. So I think the first law, inertia, part of the one. And then the inertia bit is maybe needs explanation. So if something is inert, it means it's not moving. So that's inertia.
Okay.
when an inert gas does not react, right? For your chemistry, you know your noble gases are your inert gases. Okay, Newton's second. Newton's second. Newton's second. Well, I like to remember Newton's second as an equation. And it's this equation. So if you just you go to your formula sheet, this is the main force equation. Force equals mass times acceleration. Okay, this is quite easy to explain. Let's say I've got this cell phone here, and I throw it against the wall. It's going to apply a force to the wall. That's a product of its mass, how big it is, and how fast it's going, with the acceleration. Not how fast it's going, how much it's accelerating. So if I take a bigger object and I throw that the same with the same acceleration, it's going to be a larger force. But now when I'm learning my definition, I actually have to rearrange this, because Newton's second wants us to take into account acceleration first. Because what we want to do is we want to now change our thinking from, okay, when an object accelerates, so say I have a car and I push the car. The harder I push it, the more force I apply, the more it accelerates. But if my car is heavier, it's going to accelerate less if I apply that same force. Because imagine a massive car and me trying to push it. It's not going to accelerate very fast. A light car can accelerate faster. So it's directly proportional to my force, but indirectly proportional to its mass. So I rearrange this equation to say A equals F. I take M to the other side, it goes to the bottom. And then all I do, we'll check the official definition, but all I would do is say the acceleration of an object, and we'll see how close this is to the actual answer. The acceleration of an object is directly proportional to the force, right? Because the force is on top. I'm going to say to the force applied on that object. And indirectly proportional to the mass of the object. Okay, so what's the official definition?
So the official one says when a net force F net is applied to an object of mass m, it accelerates in the direction of the net force. The acceleration A is directly proportional to the net force and inversely proportional to the mass.
Okay, one more time.
When a net force, F net, is applied to an object of mass m, it accelerates in the direction of the net force. The acceleration A is directly proportional to the net force and inversely proportional to the mass.
Okay. So we need to just change inverse, or you're probably very, very right. We say inversely proportional, right?
Yeah, inversely proportional to the mass.
So you just have to say at the beginning, when a net force is applied to an object. When a net force is applied to an object, the acceleration of the object is directly proportional to the net force.
Yes, is directly proportional to the net force.
Applied to that object. Okay.
Mm-hmm.
That doesn't have to be like 1,000% accurate, 100%, but it's
Yeah.
this would be enough. Quite a long one.
Okay.
But we can see
Yeah, it is.
the learning the equation is much easier. And then when you have the equation and you turn it to that, it gives you a framework in which to study that definition.
Yeah.
Okay. The last law is the famous one, Newton's third.
Yeah.
So this is the one that's often kind of misquoted in movies and stuff. Newton's third law, which is quoted as every action has an equal and opposite reaction. Okay, so in the movies they talk about this, you know, when someone does something, then there's actions have consequences, basically.
Mm-hmm.
So they'll often just quote it in the movies and that. But really what it is that if I apply a force to something, that's going to push a force back, and it's going to be the same force. Now, this is quite difficult to get your head around sometimes, because if let's say this wall behind me, right? It's a pretty strong wall. So you could say, well, I would never be able to push that wall down. So I can never, it's always going to apply a bigger force to me. Well, that's not true, because the force that the wall applies to me is dependent on the force I apply on the wall. So in other words, if I'm not doing anything to that wall, it's not applying a force to me. When I start pushing on the wall, it just matches that force equally. If I push harder, the wall pushes back harder. So the wall, if I was incredibly strong, I would be able to eventually maybe push the wall over. But the law will still apply, even though there's a resulting force. And this helps to explain why, say in cricket, when you hit the ball, so the ball's coming towards the cricket bat, and then the player will then swing the bat, and he'll hit the cricket ball, and it'll travel in a huge direction. I'm sorry, in another direction, but it'll travel for a six or to the boundary, but it'll go far. And then you say, well, if the bat and the ball had the same force, then surely the ball would just not move. The bat and the ball would move. But look at Newton's second law. Acceleration equals force over mass. Well, what do we notice? The ball, the cricket ball, is like maybe, I don't know, 150 grams. But then the cricket bat, which may be kind of, 3 kilograms. And then not only that, it's also, you've got to look at the weight of the cricketer's arms, because it's all one motion. And so the same force is being applied, but the acceleration, which would be proportional to that force of the ball, will be much higher because it's much lighter. So even though the forces are the same, the acceleration of the ball will be higher. So that's Newton's third law. So another kind of example of why the Newton's third law is difficult some people to understand is if I'm standing on the earth, which is trillions of kilograms, and yet the earth can only apply a force on me that I apply back onto the earth. So it doesn't matter the weight of the object. The force is still the same. So if I am standing on the ground, the normal force from the earth is equal to the gravitational force times my mass of me standing on the ground. So these great bodies, they just match the force that you apply. So let's look at what is the official definition.
So for Newton's third law, the official definition says when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A.
Okay. Let me say object B.
Object B exerts,
and exerts a force equal and
opposite,
yeah. Equal in magnitude and opposite?
Yes.
Okay. Cool. So those are the three laws. So first law, inertia. An object in motion, or an object at rest or in uniform motion remains at rest or in uniform motion, whatever it is. Second law, the force equals mass times acceleration. So we just learn the equation. And then the third law, one from the movies, actions have consequences. Every action has an equal and opposite reaction. And our official definition is just object A exerts a force on object B exerts on A, maybe equal to magnitude and opposite. Okay, so yeah, those are the three laws. And what happens is you'll often get asked these laws, and then with the second one, when I ask you Newton's second law, probably going to ask you an equation involving force equals ma, F equals ma. So we can end it there on the Newton's three laws.